Hello, welcome to Homework 1, Part 4. Today we are going to be going over Part 4 of Homework 1, so let's check out the problem. So our problem is an open container containing initially 1 atmosphere and 298 Kelvin containing 1 kilogram of water. The container is sealed without removing the air, then heated to a pressure of 2 bars, at which point the vapor space contained 1.3 moles of water. So it wants us to find the final temperature and the final volume of the container. So how we are going to do that, and I took the liberty of writing down our initial values and our unknowns. So our initial values are the initial pressure is 101,325 pascals. Our initial temperature, 298 Kelvin. Our milliliters, not milliliters. The mass of the liquid is 1 kilogram. The final pressure is 200,000 pascals. That's also 2 bars. The moles of the vapor is 0.3. And then our 2 unknowns. So how are we going about solving this problem? Obviously we have 2 unknowns, so eventually we're going to need 2 equations. But it's impossible to find just 2 equations that we can plug numbers in and solve this problem. So what we are going to have to do is create a series of equations. They don't necessarily have to string together, but they have to relate to one another. And by doing that, we will be able to relate a bunch of equations together to eventually solve for these 2 unknowns. So I'm writing on my trusty, borrowed my girlfriend's iPad so I could do this. So this is pretty nifty instead of just writing on a piece of paper. So let's start relating equations to one another. So let's just start with volume. So the total volume is going to be equal to the volume of the vapor plus the volume of the liquid. And it's going to take a second to update. There it is. So we have that. So that's one equation. Let's do another one. So the mass of the water total is going to be equivalent to the mass of the vapor plus the mass of the liquid. Now wait for it to, hold on, wait for it, come on. So we were given the moles of vapor was 0.3. We can convert those moles to mass using the molar mass of water. I really wish this would update. So we're going to do that. There we go. So let's do that. So N, let's do that off to the side. N moles of vapor equals 0.3 equals the mass of vapor over the molar mass of water, which is 18 times 10 to the negative third. So then we can rewrite that as the mass of the vapor is equivalent to 0.3 times 10 to the negative third, 18 times 10 to the negative third. Alright, there we go. So let's do pressure. So pressure final, which we already know, is equal to the pressure, the partial pressure of the vapor plus the partial pressure of the liquid. Alright, well now let's relate, now let's make equations for the partial pressure of the vapor and the liquid. Let's do the liquid first. We can do the liquid using the Antoine equation. So let's do that. We know the Antoine equation is log base 10 times P equals A minus B over C plus T. So the pressure of the liquid is equal to 10 to the power of A minus B, because we have the log base 10, so that's going to be 10 to the power of B over C plus the final temperature. That is going to update eventually. I'm sorry, I don't know why this is being so slow. I was doing it earlier and it was being quite speedy, but must be experiencing an internet problem. Wait for it. It wants to do it sometimes, and then other times it gets mad. There it is. Oh, there it is. Okay. So then let's do the vapor partial pressure. So the vapor partial pressure, we are going to use the ideal gas law, because we're assuming that this vapor is an ideal gas. So in order to do that, we are going to have to, let's just write that off to the side. So PV equals nRT. We're going to have to do a little converting of the gas law to get V onto the other side. So we're going to have to divide both sides by V. So that is going to be the moles of vapor initial times RT over, actually, hold on. Let's just do N moles vapor over the vapor. Perfect. Okay. So we have an equation relating the volume of vapor to the pressure of vapor. Now let's find an equation where we can relate something to the volume of the liquid, since we already have something for the volume of the vapor. So the volume of the liquid, so we know that density, that's a horrible density, it's supposed to look like a P. Alright, so that's just what I'm going to use for the density symbol, because if I draw a perfect P, it's going to look like all my other variables, so just accept that as density. I know it sucks, but bear with me. So we know that density equals mass over volume, so then we can relate that to the volume of the liquid. So that would be volume of the liquid is equal to the mass total minus the mass, so we want mass of liquid up there, so we want mass total minus mass of the vapor all over the density of H2O. Obviously we want that to be liquid. But remember, up here we already solved for mass vapor. So why don't we just go ahead and throw that into this equation. So that is going to be volume of liquid water is equal to mass, oh, what just happened? It's equal to, no, what happened? Hold on, technical difficulties. Seem to have been disconnected. Hold on. There we go. Okay. So volume of the liquid is equal to the mass total minus 0.3 times 18 times 10 to the negative 3, and that is over. My headset just died. Alright, so still have audio. Okay, good. So 10 to the negative 3 over the density of water liquid. Okay, perfect. Now we have an equation relating the volume of liquid to the density, and that is good. So now, some equations that still need relating. We need to relate this moles of vapor because we don't have it related yet. So, moles of vapor initial, that's an exclamation point. That is an I. We'll wait for that to load. There it is equal to the pressure. So this is going to be another ideal gas law conversion. We are just now solving for moles instead of P like we were before. So moles is equal to the pressure at temperature initial, so pressure initial, times the volume of vapor initially, all over temperature, R times temperature initially. Right, let's wait for that to load. Perfect. So let's keep going. Let's simplify that a little bit. So moles of vapor initially, that's also another exclamation point. I don't know why I keep doing that. Is equal to this pressure initially is going to be. No, I don't want pressure. I'm sorry. I was thinking about this. I was like, this doesn't seem right. Because it's not right. This is pressure vapor initially, not just pressure initially. So that is going to be pressure initially minus pressure of the liquid initially times pressure vapor initially. So volume of vapor initially, all over R times T initially. Well, there we go. That solves the problem for that variable, so we can erase that. Now we just need an equation relating the volume, the moles of volume finally to this same equation, so we can just do that real quick. Moles of vapor finally equals 0.3 because we were given that, equals the pressure of the vapor at the end finally plus the volume of the vapor finally, all over R times T finally. Okay, those are all the equations that I can think of that we can relate to this problem. But now you might be thinking, well, this doesn't narrow down two equations that we can use to solve for two variables. Well, actually it does. The two, let me pick a good color. Let's pick, I like purple. The two equations that we are going to use to solve this problem are the pressure final equals 200,000 pascals and the moles of vapor final equals 0.3. Now you might be asking yourself, well, that doesn't make any sense because those don't relate to what we need to solve at all. Well, here's the thing. Oh, I just did it again. I just did it again. Hold on. I don't know what I keep hitting. There it is. Okay. So you might be thinking, well, here, let me start this. You might be thinking, well, how does that make any sense? Well, it makes sense because we are going to set these equal to 0. So P final equals 2,000 and n that equals 0. Moles of vapor equals 0.3. Please load, you dang computer. So while that's loading, we are going to set these equations equal to 0 and have all of the rest of the equations we just made relate to this equation. So when we go to code, it is going to look like this. It's going to look like pressure final minus pressure final desired equals 0. It's not actually going to look like equals 0, but we'll explain as we get there. So that minus moles of vapor desired equals 0. Underscore desired. So you might be wondering, well, what's this desired? This desired is what is the variable we are going to put in Python. So this desired pressure final desired is going to be 200,000, and then moles vapor desired is going to be our 0.3. So then we are going to relate all of the rest of these equations to these two. So what that's going to do, since this is set to 0, when all of these equations are related to these two, the values that these are to equal 0 will spit out our two, oh my, I just did it again, we'll spit out our unknowns. And I know that might be confusing right now, but it will make more sense when we go code it. So basically this is what we're going to put into Python. We are going to relate all of these, not all of these, but the core ones, to these inequalities down here, these equal to 0, not inequalities, these equations set equal to 0, and that will allow us to solve for these two values. I will be explaining that in Python momentarily. Stop. How's it going? Now for the second part of this video, we are going to be doing the code to solve for our unknowns. So if I look down, I am referencing the notes. Focus. I'm referencing what I just did on this iPad because I can't remember all of those functions we just wrote down to enter into this code. So that is what I'm referencing. Alright. Now to the code. Okay. So we imported using the git command and clone. We imported code from Dr. Co that allows us to use code that he created to use things to solve for this homework, such as the density and the vapor pressure functions. So I imported that in the system, and then I set a path to it using this command to the content that he added, that he gave to us. So now I'm going to import tools. I'm importing these tools from that to allow us to use them. And we're gonna put it as CHE, so every time we reference it, we don't have to do tools.che. And then from scipy.optimize import root. We have to import the root function from scipy.optimize so that when we define our equations, it's going to create a vector, and this root will allow us to pull those two unknowns out of the vector. And then we are going to name the variable p or ch tools, and this is water. This will allow us to use the functions from CHE tools, and they will pertain to water. So that's actually very helpful. Make sure that all works. That all works. We're good to go. Alright, so now we're going to define our initial variables that we are given. So if I can reference those here, we'll do pressure initial is equal to 101,325. That is pascals. The next one is temperature initial. That is equal to 298. That was Kelvin. Next one was mass of the liquid total. So that is equal to 1. That is in kilograms. I just got an email. Next, we want, because remember when last part of the video, so a minute ago, when I said that we were going to set the pressure and the moles of vapor equal to 0. So now instead of just doing pressure final, we need to do pressure final desired. That is equal to 200,000. 1, 2, 3, 0, 1, 2 zeros, 1, 2, 3. Okay. And that is also pascals. And then we want the moles of vapor desired as well for the same reason. Make sure I spelled desired right both times. That's important. And that is equal to 0.3. Okay. And that is all our variables. I need to add an equal sign, don't I? There we go. Alright, now we're going to define our equations. So, define equations, and that's going to be a vector, so we'll just call it vec for vector. And then we're going to unpack that vector equaling our two unknowns. So, T final, and volume total equals vec. That's not capitalized. Vec. And then, like I laid out earlier, we need to return that those two equations equal to 0. So the first one is going to be pressure final minus pressure final desired equals 0. And then NVAP, the moles of vapor minus the moles of vapor desired equals 0. Okay, very good. Now give some space to work. Alright, so the first thing I want to do, now let's look at our equations. We basically want to put all of the relationships we just wrote down on paper in code. So let's start with, what should we start with? Well, we need to do this in a way where the ones we set equal to, we're defining them. So if something is in an equation before we define it, it's not going to work. So we have to define them first before we put them in an equation. So that's why I'm trying to mull over this for a second. Alright, so we're going to define M vapor, so mass of the vapor first, because we solved that by doing the moles of vapor desired. That was multiplied by 18 to the negative 10 to the negative third. So there we go, we defined one already. Now let's look for a function that had mvap in it. We already have mass. Oh, here we go. We can do the partial pressure of the liquid is equal to P dot roll, which is, that is, no, I'm sorry, not P dot. P dot roll, RHOL is the density of density function for water. We want P that for the vapor pressure, and that was at what? So that equation was 10 to the A minus B over C plus T final. So we want that at T final. Just make sure these all work so far. All right, good. All right, now do we have one with P liquid? Okay, here we go. Let's do this one, because this, let's do moles of vapor initial, because we need that for quite a bit of them. So let's see this. Moles of vapor initial is equal to, how did that function go? Moles of vapor initial over Pi minus P pressure initial minus the vapor pressure. Alright, here we go. So the pressure initially minus P dot P vap initially. So the pressure of the vapor initially, that was multiplied by, what was that multiplied by? That was multiplied by V total, so the total volume, minus the mass total divided by the density of water. So that's what P dot RHOL means. But that is at temperature initial, so we need to specify that. Now let's make sure we have all our parentheses taken care of. We need one here. 1, 2, 3, 1, 2, 3, 4. We have one extra. Is that good? That, alright, it likes that. Okay. So now I just added this equation, but as you can see, I don't have V total defined. Actually, yes, I do. It's right here. I don't have mass total defined yet. So let's define mass total, because we need to do that. So mass total. No, I don't even know what I'm saying. We do have mass total defined. Mass total is up here. So shift enter that. That is good. Alright, what's next? Let's do pressure of the partial pressure of the vapor. Why don't we? So partial pressure of the vapor is what we just did. So that actually is perfect. Is the moles of vapor initially times R times T final over the volume of the vapor. Okay, do we have volume of vapor defined yet? We don't. Alright, let's do that. Volume of vapor is going to be V total minus volume of liquid. Do we have volume of liquid defined yet? I don't think we do. Let's do that. You see, once you do one and you keep doing them, you realize what you need to do, so then you just work backwards. Volume of liquid from our chart we did earlier is the mass total minus the mass of the vapor. So we just solved for that up here, so we can just put that in instead of having to do that whole solution, that whole problem right inside of it. And then this is also times the divided by the density of water at final temperature. Alright, so that V liquid, we got V liquid, V vap, we got P vap. Alright, then we need to define pressure final. I know we already have pressure final, but we don't we want this pressure final to be independent. So pressure final equals the pressure of vapor, which we just did, minus the pressure of liquid, which we have up here. Okay, then we need to define NVAP, independent from NVAP desired. So NVAP is the moles of vapor in the final position. So that is the function. We had that as the pressure, the partial pressure of the vapor times temperature at temperature final, and then that was multiplied by the volume of the vapor, right? Okay. And that was divided by R times T final. Shift enter. Okay. Make sure we have everything. Make sure, double check our sources. Make sure we're not missing any functions. Alright, it all checks out. Okay, now that we have all of our functions defined, we need to root, or take the root, or pull the root out, or use the root function to pull out our solutions. So we're going to do that. So the root of the equation, or the equation vector, then we need to make an initial guess. So since our initial guess for the two variables that we're pulling out, so final temperature and the total volume. Since our starting temperature was 298 Kelvin, but remember the problem was closing the system and heating it and increasing pressure, I think the heat's going to go up, so I'm just going to throw out 350 Kelvin. And then, since the heat and the pressure is going up, I expect the volume to go down. So I think the volume is going to be 0.2. Let's try that. Yes. Okay. All right, here we go. Must have messed something up. This is going to be interesting. Maybe no space here. Okay, I got rid of that. No, it didn't. Alright, it doesn't like the NVAP one at the end here. Oh my goodness, guys, I didn't specify R. So obviously we have to put in the gas constant. So R is equal to 8.314. Shift enter. Shift enter. Shift enter. Alright. Okay. After a long time running, I discovered the solution to my issue. So you see here, I didn't ever specify what the mass of liquid was. So let's put that in. So mass of liquid is mass total minus mass of the vapor. So now that we have that, what did I just do? Nope, this needs to be above this. Hold on. We're going to Control C that and delete it. Delete that space. This needs to go there. Nope. There. Okay. So mass of liquid equals mass total minus mass vapor. So now we can replace this with the mass of the liquid, and that should solve our problem. There we go. Our temperature is 366 degrees Kelvin, and our volume total is 0.1 grams, kilograms. Thank you very much for watching.